Hi, my name is Jackson Wise, and this is my final project for Engineering V14. For my final project, I decided to make a program for solving inverse kinematics. To explain what inverse kinematics is, I'll give you an example. Often in factories, you'll see these big industrial robot arms. They'll usually have a spot welder or a paint sprayer or some kind of tool at the end. In order for them to properly use that tool to interact with the workspace, let's say weld the right spot, paint the right part, they need to know where it's located. You can compute the location of the tool, called the end effector, based on the angles at each joint and the length of each arm segment. This is a process called forward kinematics. Inverse kinematics is basically the opposite of this. You use the location of the end effector and you find what angles will result in that location. Inverse kinematics problems can get really difficult as the arm gets more complex, so I wanted to make a program that would work no matter how many joints are in the arm. So the first step in the program is to get the data for the new arm. It gets it from an Excel spreadsheet formatted like this. So in the first column, you have the length of each segment of the arm. This can be different for each segment. I have it set all to 1. It doesn't really matter. And then in the right column, you have the limit on how far each segment can rotate. Here, each segment can rotate out 90 degrees and form a right angle with the last. You don't need to put in how many segments there are. It automatically figures all that out just from looking at the spreadsheet. Here, it just uses a while loop to make sure you put in the name of a spreadsheet that's actually in the same folder. If you just typed something at random, like this, it'll tell you to use a valid name. Let's use this one I already made. 5 joint 90. It's got 5 joints and they can each rotate 90 degrees. So it'll read the spreadsheet for the arm and convert it into the variables it needs. Next, it's going to ask for the target coordinates. So let's say 10, 10, 20. It'll plot that as a black circle, and then it'll build the arm in its base configuration, which is just straight up. Now you can see that it's stopped. That's because the target point we've chosen is further away than the arm can reach. It'll tell you that and you'll have to try again. So let's try this again. Well, first let's clear everything. Let's try this again with the new target position. 5 joint 90. Then let's do 2, 3, 2. So you can see that took a few seconds, and we've got a graph here showing our initial configuration in blue, just straight up again, our target as a black circle, and now our final configuration in red. Let's look at how it did that. Basically, we have a loop here that's going to repeat until the end effector is within an acceptable distance from our target. I have the threshold set to 0.05, but that could be set to whatever, depending on how accurate you want it to be and how fast you want it to run. So every time the while loop runs, it tests to find the gradient, which is basically what changes in all the angles will cause the distance to increase the most. It then moves them in the opposite direction so that the distance decreases, and then it goes back and tests again until the distance is within the threshold. To figure out whether the angles need to increase or decrease, you have these two for loops. It goes into the first one, it resets TXG, which is basically a matrix with all the angles we're using for testing the X angles. It sets it equal to TX, the current X angles, and then it adds delta X to one of those angles. Delta X is just an arbitrarily small number. I think I have it set to 0.01. The next for loop builds the arm with just that one X angle changed. It then takes the distance between the end effector with the angle changed and the target and stores that as FGX under index M. Then it does the same thing for the angles around the y and z axes. Once it's done with that, it estimates the gradients based on the distances from the tests and the actual distance, and then it moves the angles in the opposite direction. Once that, it builds an arm with the updated angles and checks the distance again. It'll give a little message every time it updates, just so you know it hasn't broken or anything and you can track the progress. Once it gets the distance within the threshold, it'll exit the loop, build the arm in its final configuration with the new angles, and give you a little complete. So one thing that's pretty interesting about the implementation is up here. It's called the learning rate. It's pretty much how far the angle will change against the gradient each time. A lot of people have trouble with this because if it's too small, the program will have to run more iterations and it'll end up slower. But if it's too large, it'll move faster, but it could jump over the target point and it might not be precise enough to get within the threshold. So to solve that, I used an adaptive learning rate. It'll start out large so that it can move quickly, and it'll gradually decrease along a cosine curve so that it can get more precise as time moves on. Then, after a certain number of iterations, it'll reset back to the maximum and repeat the cycle. As another example, here's the program running with a 100 segment arm, each segment 0.1 in length.